And so it would seem that there's kind of a natural tendency for stuff to become less and less unique and turn, therefore, into more symmetrical stuff.
Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert de Nameland, who has been the greatest living philosopher before me. So in this video, I want to continue this line of reasoning that I've started with my video, Does Information Have Mass? And we shall consider a couple of more papers by Melvin Vopson that deal with information specifically. And in fact, spoiler alert, Vopson actually proposes one extra new law of physics that deals with information. So without further ado, let's roll.
Today we shall consider this paper, and then slightly later this paper, at least partly. And I'm looking into my own downloaded PDFs because, as you can see, I made some notes over here, but I'll link all of what I'm showing to you on the screen in the description to the video, so you can read them on your own if you wish. They are free to read after all. Anyway, so we're dealing with a paper by Melvin Vopson once again. This time we're talking about, last time it was this video, Does Information Have Mass? Where we talked about his idea about the mass-energy information equivalence based on the Landauer's principle, okay? But right now we're talking about a law that he proposes, okay, which is called the second law of information dynamics. It is basically a sort of a tribute to the second law of thermodynamics, okay? It's not like there was a first law of information dynamics to begin with. It's just that, again, it's kind of a mirror of the second law of thermodynamics. But let's proceed and take a look at what it actually says. So this is my, once again, note. So the second law of thermodynamics, according to Melvin Vopson, I mean, he's the author of the law, if you wish, requires the information entropy to remain constant or to decrease over time, okay? Then this is exactly the opposite to the evolution of the physical entropy. So in this video, I shall repeat some of the points I've made in the previous one, on that other paper by Vopson, but still they are worth repeating, so let's take a look what we have here. So again, Landauer, and in case you didn't understand anything that was written here, like we'll proceed and try to discuss this further down the road. So Landauer suggested that logical irreversibility, must be equivalent to physical irreversibility, okay? And right away, again, remember in the last video on this topic, I've already voiced my concerns about the Landauer's principle in the first place, but strictly speaking, with respect to this statement, right, that logical irreversibility must be equivalent to physical irreversibility. This is just wrong, okay? And I have a link to prove it to you if you wish. Again, I'm going to link this in the description. So a concrete objection to Landauer's principle, where the author states that, Wait. Logical irreversibility does not necessarily imply thermodynamical irreversibility, okay? So this statement is just wrong, okay? And once again, I'll have some more criticism of the points Vopson makes sometime later, but let's proceed. So he states that erase operation that deletes a bit of information is irreversible, and then it must dissipate a small energy that comes. I actually agree with this, mostly at the very least, if we are to believe Landauer in the first place. But he states that this extra energy comes from the memory bit itself. And if you remember my previous video, once again, this one, I claim that no, I don't think it comes from the memory bit itself. I think it comes from the machine that does the erasing, okay? Because it provides some work, otherwise the erasure wouldn't have happened, and therefore this work is the source of energy for that is being released during the erasure, okay? And then blah, 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 we're talking about something else. Again, we're only looking at my comments, to be frank, but hopefully you'll get the idea when we'll get to the idea, so to speak, of the paper, I mean. Anyway, so one of the points he makes is that the universe is fundamentally mathematical and can be seen as emerging from information. Once again, you probably know my stance on this. I actually have the reverse view. I think that mathematics is our own invention, is our own tool, tool to describe the universe rather than something fundamental to the universe itself, right? And I actually even compare mathematics to a conspiracy theory here, right? And there's some secret cabal of numbers and vectors and tensors and inequalities and differential equations governing the universe, supposedly, right? So yeah, I still think it's a conspiratorial thinking in its essence. Anyway, closer to the topic of the paper, okay? So the author states that the physical entropy of the system is characteristic of the non-information bearing microstates within the system. And my criticism here would be is that there is no such thing as non-information bearing microstates within the system, in the sense that there's no such notion, you know, nobody says that. That there are information-bearing microstates and there are non-information-bearing microstates. And once again, we are returning to the point I made in a previous video that information is not physical to begin with, okay? That's why nobody ever has distinguished information-bearing microstates and non-information-bearing microstates, because for nature they are equivalent, right? Whether a microstate has or has not an information is for us to agree upon, right? If I say, well, let us treat this particular state as having this particular piece of information and this particular state as having no information whatsoever, is again, it's our convention, right? It's our agreement between each other. It's not inherent to the universe or nature itself, like however you want to put it, right? That's kind of my point here. So this formulation is incredibly suspicious to begin with. And again, he continues, the additional n bits of information created within our test system represent n additional microstates superimposed onto the existing physical microstates. Like, once again, the author tries to sort of introduce a new entity, sort of, in order to promote his own agenda, I would say, you know, like he has something he wants to prove, and therefore he has to adjust even the terminology. Like, nobody talks about, as I've said, information-bearing microstates or non-information-bearing microstates, but he has to introduce it in order to, in quotation marks, prove his point, all right? And he superimposes them onto the existing physical microstates. It's actually good that at least he recognizes that physical microstates are different from information microstates, right? Because information microstates only exist in our head, right? And whereas physical ones actually exist in the physical world. Sadly, though, I have to say, that's not the conclusion he arrives at, all right? And let's take a look further. So the total entropy of the system is now the sum of the initial physical entropy, I'm all right with that, and the newly created entropy of information, all right? So nobody says that. I have to stress. So Shannon, and he quotes Shannon sometime later. So in his paper here, the mathematical theory of communication, where he introduces this idea of entropy of information that Vopson uses quite a lot, actually, he never talks about physical implementation of this, okay? So he only talks about the uncertainty and the amount of uncertainty that is being resolved for us when we receive the signal, okay? So completely irrespective of what is happening physically, right? And Vopson is trying to sort of bridge this gap between the world of information, which exists only in our heads, that is my claim, and the world of physics, which exists physically, you know. So Shannon only talks about what exists in our head in this paper, all right? And Vopson is trying to drag this into the physical world. And my big claim is that it's impossible. Like, you cannot do this. You cannot say that the entropy of the system is equal to physical plus informational, because informational is not conventional, or is it conventional? Yeah, conventional. Like, it's a matter of agreement. The physical entropy is an objective value. The information entropy is not, okay? At least that would be my claim. Yeah, well, even if you disagree with me fundamentally, consider this. Like, in order to even define the information entropy, again, for example, as Shannon does, we need to know the probabilities, right? So how would we know probabilities? Well, that's a big question. I don't necessarily have an answer right now for you, even to reinforce my own point, to be fair. But still, you know, we have to have some sort of a picture of what is going on in order to ascribe certain probabilities to these processes and blah, 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 and calculate this information entropy. But regardless, this is not the central point. This isn't even the central point of this paper. I want to get to it, okay? So let's continue. So here we're introducing this actual information entropy that I just showed you, right? And then again, Vopson refers to these information-bearing microstates. I once again emphasize nobody uses this term because there is just entropy. And what Shannon calls information entropy only exists in our head, okay? In the physical world, there is just entropy. And you cannot decompose it into two, how do you call it? Not multipliers. God damn, what's the word? You get it. Two terms, okay? So, and the reference he gives here is for himself, actually, right? So, once again, nobody uses this term, as I've said, except for Vopson. For some reason. So, but anyway, he introduces this information entropy based on a Shannon entropy. This is the Shannon bit, and then he just multiplies it for some constant multiplier, actually, this time. Okay, so n is the number of cells where bits could be written, roughly speaking. Okay, and these are the probabilities of a certain like 1 or 0, for example, right? And here we have n is the number of possible values, right? So for example, for bits strictly, we'll have n, the small n equals to 2, right? And then we calculate the probabilities of finding a 0 or 1, and we can calculate this value, okay? And then multiply by the number of cells where these bits appear, right? Yeah, so the properties of this Shannon's information entropy, really, like, information entropy is a really bad term, I think, in this respect. Like, what we're really talking about, so I'll try to reformulate it in plain language so you would at least kind of understand what we're talking about. It's the amount, it's really just information, okay? It's really just the amount of information that can be potentially decoded, or actually is not decoded, encoded, right? Written. It's the amount of information written in this particular system, basically. Not quite, but it's close enough for understanding, okay? So when we're talking about the information entropy, it's really just the amount of bits that is written, that are or is written in the system, okay? So he calculates, and it would be the biggest if the probabilities are equal, okay? So if ones and zeros are encountered relatively equally, it would be maximum. This amount would be maximum. So in this sense, you can call it entropy, in the sense that everything is kind of equal probability, right? So equally distributed, so to speak. But here, like, he encodes the word information here, as you can see. And you have these sequences of bits. If you use the ASCII or what ASCII2, I actually don't know how you read this. The table of correspondence of binary code to letters, okay? Yeah, so this is how it would look. So this is kind of like a magnetic tape, if you wish. So certain parts of it, certain domains are magnetized, for example, upwards, certain downwards. So which would correspond to zeros and units. It doesn't really matter which ones are which. And if you calculate this, you will get that the word information encoded in these on this magnetic tape would have this information entropy, aka just information, okay? So it's not unity. It would have been unity if we'd have an equal probability of encountering a 0 and 1. But in the word information, it's not the case, okay? Yeah. And the crucial point, what is the second law of infodynamics, informational dynamics? The crucial point is that, I'm sorry, I skipped a page. Here, actually, like, we're still considering this practical example. So a spontaneous magnetization flip due to thermal activation may happen. You know, there are fluctuations, so we can demagnetize one of those bits, you know, we can flip and blah, blah, blah. So we're looking at what's going to happen as time goes on, okay? So after a sufficiently long time, we expect magnetic grains to lose their magnetization state, all right? And it would lead to self-erasure of those bits and therefore reducing the information states n, this big N, right? So the amount of cells at our disposal would reduce because some of them would fall out of our consideration, so to speak, because they would be naturally demagnetized by intrinsic fluctuations of the system, if you wish, all right? And so the implication of this analysis is that the entropy of the information-bearing states, again, I highlight this is not a term anyone uses except Vopson, tends to decrease over time. So if you look at this formula, if you decrease n, so if some of the cells become corrupted, so to speak, demagnetized naturally, so this whole thing decreases because n is a factor here, right? However, I have some objections here already. Like, one big objection is that why aren't we considering the demagnetized bits as well? Because, like, strictly speaking, like, what is this gray thing? Is this a bunch of ones? Is this a bunch of zeros? Like, shouldn't we actually consider the entropy of this state as well, in the sense that, or rather, shouldn't we consider this state as a possibility as well, right? So we should have like 0 and 1 in case of two types of magnetization, plus something else in case of no magnetization whatsoever, shouldn't we? Right? And then I think the whole narrative will break down, right? Like, first of all, you'll have to adjust the probabilities somehow in order to take into account this third possible state of our bit, right? I'll remind you, it's not magnetized at all, magnetized up, or magnetized down, for example, right? And then n wouldn't decrease, right? And in fact, this whole thing would be bigger in case of 3 possibilities, because the probability would be smaller, right? It would be not 1/2, it would be 1/3. So this whole thing will actually increase in size. So I'm not sure how this thing will play out if you approach this situation more realistically, because take a look at this yourself. Like, even he himself says magnetization flip, right? He doesn't say demagnetization. He says flip of magnetization. So basically you've had 1 and now you'll have 0, for example, right? How would it diminish n, possibly? That's a good question, I think, right? So this is a very, very, we're walking on thin ice here, I think. This is not very strict. So you can tell that he's getting somewhere, but he knows where he's getting to, you know. It's not a rigorous proof. It's more like a how do you call it? Like a napkin style painting, not a painting, drawing, you know. Yeah. Anyway, so his point is that, well, okay, since this n diminishes, therefore the amount of information we can encode in this, aka the information entropy of Shannon, also decreases, right? Because there's this n here. And this is, spoiler alert, what he calls the second law of information dynamics, is that the amount of information we can encode into a system diminishes over time, right? So there is a tendency, if you wish, in the universe, according to the author, for this amount of possible encoded information to decrease naturally, all right, spontaneously. So as you can see, I'm not even 1/2 on board. I'm only slightly on board with this, only in the sense that it is really interesting to talk about this stuff. And spoiler alert, once again, sometime later, a few minutes later, down below, we'll take a look at the more interesting examples which look more plausible towards the case of Vopson, okay? But anyway, let's continue from here now. When the entropy of the information-bearing states once again I highlight, no one uses this term, it's a term invented by Vopson, is examined independently, you cannot do this except for in your own head, as Shannon does, we conclude that the second law manifests in reverse, so that the information entropy stays constant or decreases, meaning, you know, the physical entropy, aka just entropy, it should stay constant or increase according to second law of thermodynamics. And here, like a mirror image of that, if we introduce this artificial quantity that nobody uses except Vopson in a strict physical sense, right? Shannon uses it in informational sense purely, not talking about physics at all. Vopson tries to bring it to the realm of physics, and in the realm of physics he says, well then this information entropy will have to stay constant or decrease, right? Whereas the usual entropy stays constant or increases. So yeah, so this is what he calls the second law of information dynamics or infodynamics, and well, it doesn't really matter how you write it down mathematically. And here's an example, like what can happen. Like if you subdivide our magnetic tape into small magnetized domains, so each bit would be made up of several of those domains, and then over time, just stochastically, you know, you get a mess, right? But again, I have to repeat my point. Like, what about the demagnetization? Because on this picture, you kind of see, like, maybe it's a problem of rendering, but or maybe some of those domains are supposed to be black. Like, this is a question I'm still having, and I don't have an answer for it. So if there is such a thing as a black domain, right, not just red and blue, it means it's this third state, right, demagnetized state. So how do we count it? And why don't we count it, actually, in this paper? Because he doesn't, right? And so in the end, so we have this word information encoded here, and then it kind of naturally devolves into mess, into an unreadable mess, right? But again, my point here would be, why do we need any additional law to describe this? I mean, this is perfectly described by second law of thermodynamics, right? The regular physical entropy increases, right? The stuff gets more homogeneous. So here we've had a lot of red on this stripe and a lot of blue on this stripe, and here if you look at the same area, it's kind of mixed, right? So a normal increase of entropy has occurred. So why do you need an additional law to describe this? Is an open question, okay? I would claim you don't, right? Like, this situation does not require any acrobatics like this, okay? Like, it's described normally by normal thermodynamics, and that's it, period, okay? So that would be my response to this first example, on which Vopson is trying to prove or at least demonstrate his law. So my claim would be no additional law is needed, so point not taken, okay? The law is dismissed for now. But now we're getting into a more interesting stuff. So biological information, okay? So first of all, I have to voice my concern right away, because that would be, spoiler alert again, my own conclusion with this with regards to this particular issue. However, again, spoiler alert, later on Vopson kind of redeems himself. Like, there are still some things which look suspicious and couldn't quite be explained as simply from regular thermodynamics, for example. But still, let's stick to this for now. Biological information. So he studied so my concern here is that in biological world, you know, not only regular thermodynamics is in action, right? Because, first of all, you cannot consider a biological system as a closed system. So second law of thermodynamics is inapplicable to a biological system, because it's an open system to begin with, all right? Yeah. So this is a big concern I have, and it will surface up later on. Anyway, he considered actually the COVID virus, the SARS-CoV-2 virus genome. And he took a look at how it changes over time during the mutations with various, how do you call it, strains? Is that the word? Strains of virus, okay? And he only looked, so basically he says, okay, we've considered a case where n decreases and therefore informational entropy decreases as well. So this is kind of one demonstration in his eyes. In my eyes, it isn't, of his law, of his proposed law. And he says, well, let's consider a case where n would be constant, but this thing would decrease, perhaps, right? So he takes a look at COVID virus nucleotides, right? A, C, G, and T. Actually, I mean, the virus is RNA, so you have U instead of T, but it doesn't matter. And we consider them as kind of bits, right? So we have a sequence of those bits. It's actually, you need at least 2 bits to encode 4 letters, right? But it doesn't matter either. And he says, well, let's compare the strains of this virus which have the same amount of these letters, right? Because the new strains, or is it the word strands actually? I don't know. Probably strains. Sometimes, and actually most of the time, they actually evolve towards reducing of the n, but we'll come to that. But he says, let's consider such strands which, or strains which do not have the reduced n, and only the probabilities are different, right? And this corresponds to the process called single nucleotide polymorphism, where basically, for example, you have A, but then it during a mutation it changes into G, and everything else is the same, right? The whole code is the same. It's just that one letter is changed into another, right? Spontaneously. Yeah. So, and here's the data he uses. So a bunch of references over here. So this is the amount of mutations. This is the time in months, and this is like where the virus was. Where we got it from, and this is the Shannon information entropy. So remember that we said we need 2 bits to encode a letter, so we'd have 2 here if the probability of all 4 letters would be equal, but it isn't, right? So we have not 2, but less than 2. Yeah, and as you can see, I'll probably show you the graph. There it is. So the amount of mutations increases over time, right? Over 2 years, it's about almost 50, something like that. And if you calculate this information entropy, for some reason we divide it by Boltzmann constant. I actually don't know why. But anyway, it can be shown that it decreases, at least according to the author. I didn't check the data, actually. But in this respect, I believe that this could be the case, okay? So this looks strange, right? So it actually looks, at least on the surface, as a proof, or at least a demonstration of the second law of information dynamics, right? Because again, the information entropy of these variants decrease over time, right? Which basically means, actually, let me show you, like he actually quotes this code that he actually himself written. I have it somewhere here. I'll obviously link it as well. So what the code does is, I'm not sure it does this exactly, but the principle is the same anyway. So we for example, we have this genetic code, okay? And we take like combinations of, let's say, 3 letters, right? So we have this combination, then we have this combination, then we have this combination, so CAC, ACT, CTT, then TTA, etc. And we count all the unique combinations that we have in this genome sequence, all right? And then during a mutation, for example, this T changed into A, so we count all the unique triples once again. And then we can calculate our Shannon entropy for the first case and the second case, and we take a look whether it's increased or decreased or stayed the same. Basically, that's the point, right? And the decrease would mean that there is less combinations remaining, okay? So if during a mutation the number of these unique triplets decreased, it means that the Shannon information entropy also decreased, okay? That's the point. Or, as I reformulated it, the amount of information that can be encoded decreased, right? Because we have sort of like smaller amount of unique degrees of freedom, right? Like this is, for example, for this subset, he calculates that there are 29 distinct combinations, right? So CAT, ACT, CTT, you can see it, he's reading from the left. So 29 for this sequence, but for this sequence, it's only 26, right? Just because we've made this change. And therefore, the information entropy, aka the amount of possible information encoded here, would be lower than here, okay? Again, I'm not using this term strictly, the amount of information that we can possibly encode. I'm just using it, you know, as a proxy for people to understand what we're even talking about, okay? Yeah, so according to his research, Vopson's research, this is what is actually happening. So the more mutations this virus undergoes, the less information is possible to encode in it, okay, in its genetic code, which is kind of strange, right? So he claims that it reconfirms the second law of infodynamics, but it also points to a possible deterministic approach to genetic mutations, currently believed to be just random events. So his point here is that there is indeed this sort of, he even calls it entropic force somewhere, right? That there is a directionality to this, right? Where it's the information that has to be decreased, or information entropy, strictly speaking. So the mutations don't go randomly. They actually go in a certain direction, okay? Where it's less and less and less information that can be encoded in the virus over time as these mutations proceed. Then again, I still have doubts with respect to this, because if you think about it, it's kind of very similar still to a regular thermodynamics, right? Where you would expect a system to evolve in such a way that its information capacity would be a great way to reformulate this term, okay? So the information capacity is decreasing, right? Because there's less and less unique, for example, these 3 nucleotide combinations, right? There's less and less and less of them, and therefore there's less and less of information that can be possibly encoded. So the information capacity, I would call it, obviously the author doesn't use this word, rather this phrase, but I think I'll stick to it for now. So the information capacity decreases, but isn't this exactly what you would expect from regular thermodynamics? Once again, like we have some stochastic processes going on, which, like, you can't really read this, you know, like it's a mess. You can read this, so this has information capacity, at least some, right? And this doesn't. So you can pretty much encode anything you want with this, I mean, provided you have enough information capacity, actually, right? You can read this, you can use another convention, kind of returning to my point from the previous video, this information I amassed, right? Where I said that information is conventional. So you can arrive at a different convention where this picture wouldn't encode the word information, but rather it would encode certain number, for example, right? But anyway, there is some information capacity, right? Obviously, here. And here, there is probably none, unless you have a really sophisticated system of recognition of information, right? So yeah, so as you can see, yeah, indeed, the information capacity decreases, and the same happens for a virus, right? Yeah, and we'll return to that's the first point, and let me just add another one, which I've already stated actually when we began the consideration of biology here, is that biological systems, and a virus is a biological system. I know some people think viruses aren't alive, but I mean, it has genetic information at least, right? They do not behave as physical systems, strictly speaking, right? Again, these are open systems, and specifically, if you look at a virus that has been around for 2 years and like spread over God knows how many people, right? and undergone God knows how many mutations for God knows which factors, right? So it's not a closed system. That's what I'm saying. So you may expect arbitrary stuff to be happening to this virus, roughly speaking. Does this require a physical law to be explained? Or could it be explained by exactly Darwinian evolution? Like, is there a word Darwinian here? I don't think somewhere he mentioned that they are random, right? Mutations, right? Well, anyway, whether he did or he didn't, what I'm saying is, like, maybe it's this type of evolution of this specific virus is determined biologically, by the environmental pressures, by things like that. Like, you never know. There might be God knows how many factors that are at play here. This is not a closed system to begin with. So, by the way, interestingly, because I don't think he talks about this, but is this law only applicable to closed systems? I don't think he ever mentions this here, but this is still an open question, at least for me. First of all, I'm not even sure we need this law, again, as I've said. I'm not even sure it's true to begin with, right? But anyway, I'm still discussing this in case you're also interested in these topics as I am, okay? So there goes this first paper. I know it still leaves a lot of questions hanging, but I want to show you the second paper where we not only talk about viruses, but also some other stuff, okay? I think it's gonna be interesting, so let's spend maybe, I don't know, 10 to 15 minutes looking into this. Like, it's a much longer paper. Once again, I'll link it in the description, but we won't spend a whole lot of time on it, hopefully, okay? I don't want this video to be an hour long. I hope it to be at least less than an hour long. So, so this is basically also talking about the second law of infodynamics, but also implications for the simulated universe, okay? Anyway, I like this phrase. Despite the lack of evidence, the idea of the simulated universe is gaining traction, right? So mass energy information equivalence principle, we've already talked about it in this video specifically, where I basically say there's no such thing because information is not physical and mass and energy are. But nevertheless, Vopson claims that it appears to support the possibility of the simulated universe. And he claims the second law of infodynamics is also hints at the simulated universe hypothesis. In particular, basically the idea is, as the universe evolves, as time goes on, roughly speaking, you need less and less information to encode stuff, right? And therefore it implies kind of that, like the whatever is simulating the universe, again supposedly, according to this hypothesis, is trying to be more efficient, and therefore it kind of erases the information that is not needed. Well, of course, a natural question here would be, why would it start from an inefficient simulation to begin with, right? Couldn't like if it already has enough resources to simulate more informational capacity in this virus, for example, why wouldn't it just stay the same, right? This is a good question, I think, but nevertheless, let's proceed. So here we do the same things we've just discussed, and again, so yeah, we return to the virus, the same story, but later on he introduces a couple of more interesting stories, arguably, at least to me. But let's talk about the virus once again. So here he talks about this. It challenges the Darwinian view that genetic mutations are complete random events. I'm sorry, but this is not the Darwinian view. Darwinian view says that, the fittest survive. So yes, you can randomly mutate, but it can hinder your development and you can die, right? And if you talk about, like, God knows how many generations of this virus, then we arrive at the natural survivor bias, right? So basically only the fittest versions of this virus survive. So isn't it logical that the fittest versions would contain the least amount of information, right? Perhaps this extra, pieces of information made it inapplicable to certain environments, and therefore only the version of the virus that didn't have this extra information survived. Wouldn't it make sense? So the virus kind of evolves or devolves, whatever you prefer, to the lowest common denominator, right? So that information capacity of the genetic code of the virus itself would be lower, so that no harmful information, roughly speaking, to the virus, would be contained there, right? No random stuff. Only the solid core would remain. Wouldn't it make sense? I think it would. Do you need an additional physical law to explain this? A good question, right? Anyway, so yeah, I think this is just a plainly wrong statement. Okay, it doesn't challenge the Darwinian view. I think it's actually perfectly valid inside the Darwinian view. So we see the same graph, right? And I have to emphasize, right, the data points presented in this graph have been carefully selected to emphasize the linear trend. I actually don't know how far this statement goes, Maybe he actually thrown out huge variations and only left, a neat line. And once again, I haven't looked at the data, but regardless, let's keep going. Even if this is true, as I've said, I don't see a particular contradiction with regular thermodynamics or Darwinian evolution, considering we're dealing with a biological system to begin with. Anyway, here an interesting statement. Take a look. 98% of all the mutations that took place happened via deletion. So it's actually, we only looked here at the ones which did not delete anything, right? But most actually did, curiously. Yeah. Yeah, so basically he says it's either the deletion of nucleotides, which according to Vopson again would lose the information capacity because this N diminishes, right? The nucleotides getting thrown out, so there's less cells to encode information into, or there's a mutation that leads to recalculation of these probabilities in such a way that the information entropy, aka information capacity, according to myself, still decreases, right? Hopefully you get the point. Yeah, and he also remembers this experiment, which I've never heard about, but sounds quite interesting, where the virus was observed, some virus, over 74 generations, and it was kept isolated. So they observed the genetic mutations of the virus. So the initial virus had 4,500 base points. I assume this is nucleotides, but it could be combinations of nucleotides. And with each generation, the genome decreased in size, right? And after 74 generations, the virus evolved to only 218 base points. So once again, why don't you ascribe this to environmental pressure, right? That's first point. And secondly, even if you believe in simulated universe, how would it be more efficient for the simulated universe to generate a huge, very resource hungry virus with 4,500 base points and only then reduce it to 118? Maybe it would be more logical for the simulation to produce a simple virus first and then slowly evolve it upwards, to see whether it consumes way too much resources of the calculation, right? So I think this argument simply doesn't work. That's 2 points. And the point number 3 is, take a look, in case you're saying, well, he says ideal conditions, right? What are you talking about? Environmental pressures. But ideal conditions is also an environmental pressure. Well, first of all, who said that your opinion about the idealness of these conditions for this virus coincides with the virus's opinion on the idealness of these conditions, right? Yeah, it's also an environmental pressure. When life is too easy, people become lazy and fat and blah, 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 right? So the virus also became too lazy and fat and have been reduced to 218 base points, right? It's also an environmental pressure. So yeah, I don't think this evidence is of any conclusiveness towards the point that we actually need additional law of physics that states that some quantity which we forcibly drawn into a physical world, whereas Shannon was only talking about the informational world proper, is valid. I already forgot the beginning of this sentence, sorry. So anyway, you get my point, hopefully, right? Yeah. And now, two of the most interesting things, arguably, at least when I was reading this. So Hund's rule. So it's a rule of how atomic orbitals are filled. So long story short, I wouldn't give you a full treatment. Like if you wish, you may read it yourself. Again, so there's a bunch of rules formulated by Friedrich Hund in 1927, more like 1925 actually, but it doesn't matter, which basically describe simply how the atomic orbitals should be filled with electrons. Like if you add an electron, an extra electron, where would it go, roughly speaking, right? So if you have one electron, it's obvious it was going to be in the ground state with a random spin, let's put it this way, right? But if you add one more, where would it go? Would it go on the same orbital with just spin down to satisfy Pauli's exclusion, obviously? Or would it go up a level, right? An orbital, etc. Or if you have three, as in this example, how would they arrange themselves? Like this, or like this, or like this? Like what's the deal? So Hund's rule, plural, deal with this question, but they are empirical, right? Like we don't know, strictly speaking, where they are coming from. And the point of Vopson is that they actually, like the atomic orbitals are filled in such a way that the information capacity, I'm going to use my own term, would decrease. So basically, the atomic orbitals are filled in such a way so that the least information, to contain the least information possible, basically. Kind of like this, right? So in this respect, yeah, you can say, well, it's kind of an evidence for a simulated universe, right? Because if you need the less information you need to encode an atom, the better, right? For any simulating hardware. Regardless, so this is the point, and I think it's pretty big. Regardless of the interpretation. Like, again, as you probably have guessed already, I disagree with the interpretation that it is an evidence of certain new law of physics or whatever. But in itself, it's a pretty interesting observation. So he makes calculations here. I don't want to spend time on it again. But it looks legit. It looks legit that if you actually fill the orbitals according to Hund's rule, this would correspond to the lowest information capacity of these atoms, okay? So, yeah. Okay. So this is probably the biggest, actually, thing that Vopson produced, I would claim. Again, regardless of the interpretation. This looks legit, and it looks strange, and it requires investigation at the very least, okay? So hopefully you've learned something new today. Anyway, cosmology, right? You probably know my stance towards cosmology. Anyway, regardless of whether the universe is finite or infinite, the thermodynamic laws are equally applicable. Well, no, they aren't, you know? If the universe is open, again, if it's infinite, you cannot treat it as a closed system, right? Because infinity is not an object. Infinity is a rule of generation of objects. You cannot put infinity in your pocket, so it would become isolated, because it would overflow out of your pocket, by definition, right? It cannot be contained, and therefore it's not a closed system. So this is just plain simply wrong. So basically, all that follows in this chapter is pure scholastics, in my eyes, so it deserves zero attention, but for the sake of it, since we're here, let's take a look. So we take the first law of thermodynamics. We see the heat equals internal energy and work, right? But we say, well, the universe doesn't exchange heat with anything, and therefore it must be equal to zero. But we also know from thermodynamics that the heat, more precisely the change in heat, is equal to temperature times change in entropy. And since the temperature of the universe is a non-zero value, once again, it's scholastics in my eyes, but nevertheless, we deduce that the change in entropy is zero, right? This implies that the total entropy of the universe must be constant, and this constant entropy does not violate the second law of thermodynamics, of course, yeah, which allows the entropy to be constant over time or to increase. That is correct. However, in an expanding universe, the entropy will always increase because more possible microstates are being created via the expansion of the space itself. Like, it's just bad on so many levels, this sentence. Well, first of all, who says that the universe is expanding, right? Like, if anything, you could use this as an argument against an expanding universe. You can say that it contradicts the second law. Goodbye, you know? Secondly, who said that expansion of space leads to more possible microstates? Like, you know, it's a problem of continuum. Again, basically, long story short, all of these problems stem from infinity, right? If you treat it as an object, you arrive at contradictions, logical inconsistencies, and all the problems of this sort, right? And this is exactly what we're encountering here. So, you know, in a rod of a 1 centimeter length, there's infinite amount of points already. If you expand it twice, it's still infinite, right? But are you saying that the previous infinity was smaller than the new infinity, or what? Like, how is expansion of space leads to more possible microstates? Like, again, in case you're ready to consider infinity as an object, you will constantly face bullshit like this, all right? I tend not to do that, okay? And therefore no such paradoxes would appear. But anyway, this is called the entropic paradox. And to solve, by the way, if you're interested how you should deal with infinity, read Immanuel Kant's Critique of Pure Reason. He actually talks about infinity quite a lot there, and in quite a good way, okay? Which incidentally invalidates like half of modern mathematics, but it's a problem of modern mathematics. Again, it's not a problem of Kant. Anyway, this is called the entropic paradox, and to solve it, there are only 3 possibilities. Vopson claims the laws of thermodynamics are not valid, the universe is not expanding, and the entropy budget of the universe contains an unaccounted entropy term. The readers would agree that possibilities A and B are out of the question. Well, I wouldn't. Why? I don't know if the laws of thermodynamics are valid or not, you know? Like, in our limited experience, they seem to be valid most of the time, okay? Again, violations of the second law are known, but they're limited. The universe is not expanding. I mean, in my worldview, it isn't, okay? So I would not agree with you. The possibilities A and B are out of the question. But anyway, let's just try to wrap this up slowly. Once again, we're doing this bad stuff, according to myself. Oh, basically, so his point is, since the physical entropy does not change, right? And this entropy, or rather, since the physical entropy should rise because of expansion of space, the informational entropy should drop so that the total entropy would stay the same, basically, is his point. Or rise, yeah? Yeah, now, finally, another interesting thing. Symmetries, right? So basically his point is that the reduction of information capacity leads to symmetries, period. And I actually agree with this. However, what's the reason of reduction of information capacity is still an open question for me. Like, according to Vopson, it's a separate law of physics, basically, which he calls the second law of infodynamics, invented by himself. And according to myself, it might be just a misunderstood shadow of regular second law of thermodynamics, or even something else entirely, okay? But it's still an open question for me. Yeah. So how does it work? Well, consider triangles, right? So in order to encode, so to speak, an equilateral triangle, how many numbers do we need? It's just one, right? One number, which would be the length of its side. Everything else is predetermined, right? We know the angles are 60 degrees, and if we know one side, we know all the sides, right? So it's just one number that we need to encode an equilateral triangle. So the informational capacity of an equilateral triangle is just one number. If it's a real number, though, you may claim it's still infinite, right? Because you can have infinite decimal points. There's like this joke that an alien arrives at Earth and he conducts all kinds of experiments. He studies the planet for like, I don't know, 10 years. And then he just takes out from a pocket like a 1 meter iron rod. He makes a small cut on it in a certain spot and he flies away. And like the lesson to be learned here is that, like, well, in this small cut, he basically encoded all the information he gathered, right? Because again, for example, the ratio of the rod from one end to the cut to the other end to the cut would be a real number, which has potentially at least infinite number of decimal points, right? So you can encode in a single number an infinite amount of information, right? But anyway, if we disregard this point, it's just one number that we need. Then if we look at the isosceles or whatever, however you pronounce it, triangle, you only need 3 numbers, right? That would be an angle and 2 sides, right? I think it's 3, right? Well, whatever. Hopefully you can see the logic. And for an arbitrary triangle, you will need, what, 4 numbers or 3? At least you will need all the sides, right? And probably 1 angle as well. Well, at least to the precision of mirror imaging. Well, hopefully you get the idea, right? So the closer you are to the most symmetrical triangle, the less information content is there, right? And so, so the stuff in the universe has a preference towards this. According to Vopson, it's motivated by the efficiency of simulation, right? According to myself, it's actually sort of a quasi-Darwinian process, you know? Like this triangle is too unique, you know? It's too peculiar. Whereas this triangle is very bland. There's nothing special about it. I know that usually our intuition says it's the reverse, right? That this is the special triangle because it's so beautiful, right? But in fact, like, it has very little information. It doesn't tell you a whole lot, all right? Whereas this tells you a whole lot. Like there's at least 3 numbers here. I actually don't know, maybe 4. I mean, you have a sine theorem. What else? And blah 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 blah. At least 3 numbers, I think, are needed, right? Yeah. And here, only 1 number is needed. So there you go. You can go. Wait, what is this? Yeah, high symmetry, low information entropy, or in my terms, low information capacity. So you can make the same argument for how do you call it, quadrilaterals or whatever is the word. So the square has the least amount of information against just 1 number, the length of its side. We know all the angles are 90 and all the other sides are the same, right? And the more asymmetrical your thing becomes, the more numbers you need to describe it, right? So the more information capacity it has, the more peculiar, the more special, the more unique it is, right? And so it would seem that there's kind of a natural tendency for stuff to become less and less unique and turn, therefore, into more symmetrical stuff. So that's an interesting way to look at it. Again, Vopson doesn't talk about it, at least not in these terms, but I do. And I think, in a way, again, I don't have 100% a good argument about it, but intuitively, I kind of still feel that it's kind of the same second law of thermodynamics, you know? Like there's the stuff becomes more and more homogeneous, you know? Just equally distributed mess of everything, right? So if you have peculiar triangles, they are unique. One triangle is different from another, but all the equilateral triangles are the same. So you can't encode a whole lot in them, right? So again, in my eyes right now, it's still kind of a shadow of the regular second law of thermodynamics. Anyway, conclusions, right? So, what did I highlight here? Genetic mutations are not just random events. Again, we've discussed this already. Second law of infodynamics essentially minimizes the information content associated with any event or process in the universe. Well, yeah, if you believe that it exists, such a law, which I currently don't, but still, these are the things to think about, right? These are the things to think about. I would still claim that this can be explained by regular thermodynamics. You don't need any second laws or whatever. Actually, you don't need a second law of thermodynamics to explain it, or to describe it at the very least, right? This could be the consequence of environmental pressures or just some other biological processes. This is interesting. This is, I think it's legit. Okay. And symmetry is also interesting, and I also think it's legit. And I kind of think that the atomic stuff and symmetry, cosmology you can just ignore because it's just a bunch of bullshit to begin with, the Big Bang cosmology. And the symmetry stuff is also interesting and legit. So, yeah. So you may think about those things if you wish. I certainly will. I still don't know how to wrap my head around all of this, but I've been thinking about these topics for like a couple of decades already, and I think I will have to think about them a couple of decades more. So yeah, there you go.
Thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.